There we go. So today we're going to be looking at a few very major rules, but some of these are really, really easy to understand. So let me start with a simple one, okay? Let's say that 60% of San Diegans go to the beach, okay? And let's say that 50% of San Diegans exercise regularly. And let's say that 30%, actually let's say 25%. 25% of San Diegans do both, okay? There's a whole bunch of really simple questions I can ask right now. Tell me one question I could ask. Truly.
How many go to the beach and don't exercise?
Okay, keep going. How many maybe exercise and,
Go to the beach.
well, no, that's that.
Or, and don't go to the beach?
And maybe how many do neither? Those are all good questions. And you can just obviously answer them, right? How many people will go, 60% go to the beach and 50% exercise and 25% do both? So far we're at 135% of San Diegans. And can I just add up the numbers and manipulate them that way? No. So let's consider a Venn diagram, because it'll make what I'm going to do next so much easier. All right, so let's say this is beach and this is exercise. And what would my sample space be?
San Diego.
San Diegans. Yeah, let's keep it simple. So my sample space would be all people in San Diego. So it would be a very, very large number of people. By giving you a percentage, am I giving you a probability? Now think about this logically. Probability is always stated as a quotient. You can state it as a decimal, 0.5 for the coin flip. We say things like that, but people say 1/2. But don't we say it's going to land heads 50% of the time? So in other words, when you're doing the mathematics, you do probability as a quotient or as a decimal. You don't do probability as a percentage. Because you can't use a percentage, you have to convert it to a decimal or quotient. When people use percentages, they tend to be off by a factor of, 100, right? Because they multiply. But when you speak, think about that for a moment. Be like saying, you take the carpool lane, let's say 1 time a week. So I take the carpool lane, 0.2 probability of the time. No, you'd probably say take the carpool lane 20% of the time. You speak in percentages. Does everybody understand? So when I say 60% of San Diegans go to the beach, if I grabbed a San Diegan at random, what is the probability they go to the beach?
0.6.
0.6. You wouldn't say 60%, you'd say 0.6. That's exactly how you interpret that. I'm going to grab a San Diegan at random, and by the way, the at random is important because otherwise, if you've had statistics, it's a biased sample. I'm going to go to the beach and then grab a San Diegan at random. No, they're already at the beach. So now the probability they go to the beach is 1. Do you agree? You can't grab a beach goer and ask, do you go to the beach? And I have fun with that because I teach statistics, and one of my favorites is the biased samples. And this is actually done, this is actually published. You're in a hurry and you're trying to figure out what percentage of San Diegans are vegans. Great. So you decide, while you're grabbing lunch at Burger King, to interview everybody there to find out if they're vegans. And you go, my God, my results are nobody in San Diego's a vegan. Now, think about the logic of that. In 2004, I believe it was 2004, George W. Bush ran against John Kerry. And one of the networks, I believe it was CBS News, announced Kerry had won in a very thorough landslide at about 3 in the afternoon San Diego time. There had only been a couple of polls, a few states had closed the polls. But they had done an exit interview at the Democratic headquarters of each state. By the way, it wasn't a very close election. And they actually announced it and presented Kerry to give his speech, his acceptance speech, and he was very uncomfortable. My wife and I were watching this, and about 3 hours later he gave his concession speech because it was not a close election. But CBS News had announced that he won, and he won handily. because they interviewed people at the Democratic headquarters in multiple states. Do you think anybody had voted for the Republican at the Democratic headquarters? That's not a very good sampling. So from a statistical standpoint, you have to assume all sampling is random, that it's done correctly. Is it always done correctly?
No.
No, in the I think it was the 36 election, when FDR won in a landslide, they had the Republican candidate winning in a landslide because they called people and asked who you voted for, right? And only the wealthy owned phones, so that wasn't a very good way of doing things. So you can't ask people at the beach. But I'm gonna ask a San Diegan at random because maybe I'm gonna do it through the telephone. Maybe I'm gonna do it through email. So that's how you can interpret these. So let's put in the numbers. So clearly this would be 0.6, and this would be 0.5, and this would be 0.25, right? Using my left eye, right?
No.
Now you guys hopefully have done this before. You've done intersections. These can't be the right numbers. Because if I put the 0.6 there, what am I saying? I'm saying 60% of San Diegans go to the beach and don't exercise. I'm saying 50% exercise and don't go to the beach, and 25% do both. Now we're well over 100%. No, how do I interpret this? The whole circle has to add up to 0.6. Does that make sense? Oh, this is why Venn diagrams are so useful in this regard. So that's not 0.6 at all. What is it? 0.35. Because now I'm 0.6. What's this? 0.25. Now, who's out here?
100 minus, or 1 minus.
So, give me a number.
1.5.
Zero's here. So I am at, so now going back to Samuel's question, how many people go to the, or I'm sorry, what is the probability somebody goes to the beach and doesn't exercise? 0.35. What's the probability somebody doesn't exercise or go to the beach? 0.15. All of a sudden this became much easier, didn't it? Okay, so let A and B be events. In this case, my A could be the first one, the B could be the second one. Then the probability of A, oops, sorry. The probability of A or B. Now, when we say it, nobody says, all right, okay, I've got beachgoers and I've got people who exercise regularly. I'd like to know what is the probability somebody goes to the beach or exercises. Now I can just add up everything in there. Agreed? That'd be 0.85. Would anybody say, what's the probability somebody goes to the beach union, they exercise? Would you say that? People throw things at you. You don't say union when you're talking, you would say or. But does everyone understand that's clearly a union? You say or, and in fact, when you write the probability, you actually write the word or. So there's no ambiguity. And the answer clearly is the probability of A plus the probability of B, right? But if I add the probability of A to the probability of B, I have 1.1. That's more than there are people. What's the problem with that? I've counted the intersection twice. Now, this is correct mathematics to write it this way. I just want to make sure we all understand. This, let's start with English, and then this would clearly be intersection. Both versions are absolutely correct. Okay, and both versions are going to be in textbooks. So the probability that you did one or the other was 0.85, because that's 85% of the people in San Diego fit into some part of those circles. 15% of the people in San Diego are outside the circles. So whenever you're doing the probability of a union, you always subtract the intersection. So it's really, really simple. Now, where this gets a little convoluted is if I have more than two circles. That's a little bit tricky. I'm not worried about that one. Okay, we'll look at one like that a little bit later. That one's a little bit trickier because there are way more intersections to consider. So again, on another day. So this is actually a hugely important formula. Now, one thing that a lot of people make a mistake on, particularly in statistics, is they try to calculate an intersection. An intersection cannot be calculated, it can only be counted. You can only count how many are in the intersection, or somebody gave it to you. There's no part of this problem that you could have calculated the intersection. I had to tell you what the intersection was. But did you calculate the union? Yes. What if I had given you the union Could you work backwards and calculate the intersection? Yeah. Yeah, that's a fairly simple thing to do in that case. So let me throw a what if at you. Let me change this slightly. Okay. Actually, let me be completely different. All right. The probability of event A is 0.62. The probability of event B is 0.18, and the probability of A union B is 0.8. Can you tell me the probability of the intersection?
0.
How'd you come up with 0? Well, isn't this supposed to be 0.62 plus 0.18 minus the probability of the intersection? Isn't that what we just said? So that would make this 0. Is that possible? There's a word we used before. If two sets do not intersect, we say the sets are, you remember the word? Starts with a D.
Disjoint.
Mutually disjoint? No.
Disjoint, just disjoint. If two sets do not intersect, we say the sets are disjoint, okay? Because all of the, if I'm thinking of this as San Diegans, there's a whole bunch of San Diegans in this circle, there's a whole bunch of San Diegans in this circle, but there's nobody that are in both circles at the same time. The sets are disjoint, but I'm not calling A and B sets, I'm calling A and B events. I'm actually saying, you know, you're a San Diegan who goes to the beach. So if I pull, you know, if I sample you, that's my event that I found somebody who goes to the beach. So we use a different word in this case. We would say A and B are, I think one of you just said it, mutually exclusive events. If we're using the term events because we're doing a probability problem, then we say the events are mutually exclusive. That would be identical to saying, well, let me list all of the outcomes in each event, like the coin flip last day. If I listed every possible outcome in my events, and the events shared no common outcomes, then I'd say the sets that I just represented are disjoint sets, because the events are mutually exclusive. So everyone see those, they go hand in hand, but it's a context thing. Sets are disjoint, events are mutually exclusive. There's another word that we're going to use later that a lot of people get confused. This is the term independent. This is not, has nothing to do with it. Independence has totally different meaning and is actually quite more complicated than this. Independent and mutually exclusive are worlds apart. Think of this as just intersections. Is there an intersection or is there not an intersection? So the ability to do this problem is really simple if I have certain information. I cannot calculate an intersection. Again, I can only count an intersection. Okay? Does anybody know what the most common error that people do? And I've taught statistics for years. So somebody believes out there that to find an intersection, just multiply these two. Of the infinitely many problems that exist, that will actually work many times. But it won't work 99.999999999% of the time. No, you can't multiply anything to get an intersection. That doesn't make any sense. It doesn't work. Okay. In fact, we have an empty intersection, agreed? That times that isn't 0, so I'm pretty sure that wouldn't work in this case, would it? Yeah. So you don't calculate an intersection. So this is fairly simple. So now I want to go back to the roll of the dice. Okay? Roll a pair of fair dice. We're just going one time. I want to find the probability. Hopefully you guys wrote it down in your notes. I don't want to reproduce it. The sum is a multiple of 2 or 3. Seems like a simple enough question. Now, you can do this 2 ways. I can go to my dice roll chart and simply list every possible outcome. Okay, I have the outcome 1, 1, I have the outcome 1, 2. I can do that. I don't want to do that. It's too many. Do you agree? Of the 36 rolls, this is going to be quite a few of them, isn't it? Probably most of them. And if I list them all, that's correct. But if I list them all and there's a lot, is it possible I could miss one? I'm probably not gonna double count. I'm more likely to miss one, and therefore I'm gonna have the wrong count. No, I'd rather calculate this. It's easier. So when we did the chart of the day, I'm gonna do it this way now. Let's do sum, let's do probability. I'm gonna go sideways. 2, 3, 4, 5, 6. I did this vertically the other day. Vertical is always tricky because it's so long. 7, 8, 9, 10, 11, 12. Okay? All of my probabilities, if you remember, have denominators of 36. By the way, you can reduce every single one of the quotients if you choose. Is it wise to reduce quotients? When do you reduce? When should you reduce a quotient?
After you're done adding.
After you're all done. The answer. Most of you know this. Anybody in linear algebra, you know this, right? When you have multiple denominators and you're working with a matrix, that's the worst thing in the world because you got to combine terms. You'd prefer to have all your denominators be the same. Now, at the end of the problem, great. But we've all had, you know, I got to add up some fractions. You know, I have 2 twelfths, 3 twelfths, 4 twelfths, 6 twelfths. I'm going to add them up. So I'm going to first change them to, you know, 1/6, 1/4, 1/3, 1/2. Now I'm going to add them. No, leave them as twelfths, right? It makes it so much more complicated. So this would be 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. I want all of the sums that are multiples of 2 or 3. Well, being a multiple of 2 means what? That's easy. That means your sum is, starts with an E, ends with an N. Even, good. Okay. If your sum is a multiple of 2, it's even. Which sums are multiples of 2? Okay? So let's make this real simple. Let's call A the event that the sum is a multiple of 2. I want to define my event because then it's easier to express the probability. I can say P of A. Always define the things you're going to be calculating so that you're not having to write a paragraph instead of just a simple algebraic statement. What do you want to call B? Multiple of 3. Now, wait, hold on. Multiples of 3. That would be what? 3, 6, 9, 12. Is there a potential problem here?
Double counted 6 and 12.
I've got some that appear twice. So, what would A intersect B be? The sum is a multiple of 6. Because 6 and 12 would both be multiples of 6, which is fairly easy. Oh, I was dealing with 2 and 3. Yeah, 2 times 3 is 6. Does everyone agree with this? So what is the answer to this question? The answer to this question, now the question is, I wanted you to tell me what is the probability that my sum is a multiple of 2 or 3. Because I've clearly defined my events, I can now state it in this form. This is way easier, by the way. You always want to do this. Because everything I say now will be really simple, really concise, and it will look mathematical as opposed to me writing a long explanation that might just confuse people. So I know the answer here is P of A plus P of B minus the probability of the intersection. Now, how do I come up with any of these? You just add up the fractions. Okay, well, multiples of 2. All right, let's add those up. Be 1 plus 3 plus 5 plus 5 plus 3 plus 1 over 36. Now what would that be? What does that add up to? 18. How interesting. Exactly half the sums are even. So that means exactly half the sums are odd. Does that surprise you? No, that's, I wouldn't say it's an oh duh, but yeah, it definitely makes sense. All right, multiples of 3. Where's my multiples? Here we go. 2 plus 5 plus 4 plus 1. 12. That's kind of weird. A third of the rolls are multiples of 3, half of the rolls are multiples of 2. Guess what? A fourth of the rolls are multiples of 4. Oh my God. And not a fifth of the rolls are multiples of 5. No, I won't work. Now, how many are multiples of 6? 5 plus 1. 1/6 of the rolls are multiples of 6. Oh. You couldn't have known that before you counted, but that's kind of convenient, isn't it? So, what is my answer?
24, 36.
24 over 36. Would now be a good time to reduce? Yeah. Why didn't I reduce as I went? Because then I would have been adding halves to thirds and subtracting 6. There's no logic to that. No, leave it as 36 and then, so if I said I'm going to roll a fair pair of dice, what is the probability that my sum is a multiple of 2 or 3? 2/3. 2/3 of all the rolls are multiples of 2 or 3. Who knew? Now, there's no way you're going to guess that answer, but the calculation was very simple. I counted these, literally, didn't I? Now, could I have listed the set that included all the outcomes? Yeah, I could have done 1, 1, right? 1, 1, or I shouldn't say comma, really. 1, 1, 1, 2, 2, 1, 1, 3, 2, 2, 3, 1. I don't want to do that. Not only does it take too long, am I likely to leave one out? Yeah, I'm having to think about that now. I don't want to do that. It's easier to just count. And we have this information always readily available. Having the dice roll chart is going to be very valuable because we're going to be using that later when we do things like conditional probability. Remember I said you saw what one of the dice landed and now it changed everything? That kind of thing. It's easier to do those with the chart. But I don't need it to do this one. Any question on this? This is fairly simple stuff, okay? But it's really important that I understand that I have to consider intersections when I'm doing calculations of things that may overlap, okay? Now, why didn't I consider that here? Well, first of all, if I'm adding the numbers on the dice, there is no outcome that adds up to 2 different numbers. So if I'm finding all the outcomes that add up to 9, there were 4 of them, none of those outcomes add up to anything else, and none of the other outcomes add up to 9. So in other words, each of these would definitely be mutually exclusive, each of these outcomes. Agreed? There's no overlap. But that's if I said I want my sum to be 9. Now when I said I want my sum to simply be even, that's several of them. I want my sum to be odd, that's several of them. That's a little bit different. Now, one of the most important parts of the ability to count is understanding the big picture, my sample space. I understand how big my sample space is. Now, in this last example, I'm going to roll the dice 1 time. What's the probability that my sum is at least 3? Now, what does that mean? My sum is at least 3. That means it's this or 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 this. Are there any overlaps? No, not in this case. So I would add up this plus this plus this plus all the way down the line. My sum is at least 3. I'm going to add all those up, and I'm going to get 35 out of 36.
No, just subtract.
Wouldn't it have been a lot easier to say, well, what am I not including? That's the only one I'm leaving out. Can I look at it that way? Would that have been easier? Yes. And I'm going to show you one of the most powerful tools when it comes to probability, and that is using the complement. Now, I have to understand what the sample space is. Complement only has meaning if I understand the whole. So if my universal set is the people in this classroom, then if I said, what's the complement of the set that includes Mandy and Zachary, you'd say it's the set that includes everybody else in the classroom, right? Not on planet Earth or, you know. So if I understand my sample space, the complement is simply everything else, okay? If we agree, okay, if A and B are mutually exclusive, then the probability of A intersect B is 0. Okay, that's an absolute, because that's the definition. If 2 sets are disjoint, the probability of their intersection is also 0. That, again, the same language. That's not the issue. It comes down to this step. So, what if the probability of A plus the probability of B Let me erase all this. Or I'm sorry, let me restate that. What if the probability of A union B is 1 and the probability of A intersect B is 0? I'm going very, very specific case here. The probability of the union is 1, but doesn't that mean the probability of A plus the probability of B minus the probability of the intersection? But I'm saying the probability of the intersection is 0.
A equals B complement.
So if I was to draw this using a Venn diagram, and I'm going to use language we've already introduced. Here's my sample space. Here's A, here's B. It's that simple. I don't need circles. I'm either in A or I'm in B because together they made up the whole and there's no overlap. By the way, this statement here does not mean there isn't overlap. There could still be overlap in this statement. The two together means there's no overlap because there's no intersection. So, not having an intersection, I could have two small circles. Don't write this. I could have this circle and this circle, they don't intersect. But together, do they make the whole? No, not the small circles. So together they make the whole, there's no intersection. Then we'd say A and B are disjoint sets, mutually exclusive events. But more importantly, as Samuel said, in this case, I can say that B is A complement or A is B complement. They would be saying the same thing. And if that's the case, this is huge. This is huge. What makes something a complement? First of all, it's the everything else, but it also means there's no overlap. What is the definition of a contradiction? Do you remember? When something and its negation are both claimed to be true at the same time, that's the definition of a contradiction. Well, in terms of statements, the negation of a statement is the equivalent of the complement of a set or the complement of an event. It's the everything else. It's not being in that set. So if I said, I'm thinking of U2, the complement would be not U2. But what is not U2? Everybody else. Okay? So does that give us a convenient formula? Yes, it does. It's a hugely convenient formula. If, let's say, B equals A complement, then the probability of A is equal to 1 minus the probability of A complement. In my picture, A and B union to everything and they intersected to nothing. So we agreed that B has to be the complement of A. This formula right here is one of the most powerful and useful formulas. It is a really simple rule. Again, I've taught stats for a million years, and we do a lot of probability. And the question you always ask is, well, when do I use complement? If calculating the complement of something is simpler than calculating the thing itself, what's the probability of getting a sum of at least 3? That required a lot of numbers, didn't it? You had to add up a lot of numbers. What's the complement of that? The sum added up to only 2. That's easier to calculate. If the complement is easier to calculate than whatever it is you're being asked, then always do the complement. But then subtract your result from 1. Remember, you're doing probability here. If I was simply counting the number of things in the event, then I would subtract it from the number of things in the sample space. Agreed? Because what is this? This is the number of things in A divided by the number of things in the sample space. This is the number of things not in A divided by the number of things in the sample space, and then those two together would have to add up to 1. So this is very convenient. So in the last example, you would have said my answer is 1 minus 1 over 36. That just makes it easier. But this also gives us rise to an entire new set of types of problems. This is one of my favorite types of problems. It's called the mathematics of at least 1. Okay? Now, there are certain rules. If I am performing an experiment and the probability is staying the same, I'm flipping a coin. I'm rolling the dice. I'm pick a card, any card, but I may be putting the card back in. Okay, so I'm going to pick a card again maybe later. Maybe I'm going to pick a card later. If I'm doing something over and over again and the probability is not changing, Now, that's very important because we're gonna talk about situations where the probability does change. We talked about with and without replacement last day. If I'm doing something over and over again, can you think of something in life, especially if you're a gambler, where you could do it over and over again and the probability will remain the same every time you do it? Nothing will change. I just gave you an example, flipping a coin, rolling the dice. Anybody ever do one of these things?
Slot machine.
Slot machines. Yeah, that's by far the most common gambling device there. It's not even comparable. Has anybody ever been to a casino? I mean, you were just using the bathroom, I know, but has you been to a casino? What do you see? You see every slot machine taken up with people, usually they've been there way too long and they're kind of wide. That's my experience. They have buckets usually of nickels or quarters, and they're feeding it in, going over and over again. And they will be there all day. It is unbelievable. You've seen that. It's kind of a scary thing. But people will be there and they'll be there all day and hoping to win. Will somebody win? Yes. Eventually somebody's going to win. It probably won't be you, but somebody's going to win. But would you say that every time you pull the slot, you have the same probability of winning every single time? Yeah. Because if you didn't, that would mean that somehow there's cheating going on. It has to be a brand new game every single time. That's very important that we understand that. But if I do a slot machine one time, I'm not going to win. But what if I do it, I said, I've got all day. I got some time to kill. I'm picking up somebody at the airport in Vegas at night. It's 8 in the morning and I've got 10,000 quarters. I don't know, I'm going to sit there all day. Maybe my probability of winning just got a little bit better. Now, my probability of winning on any individual try is not very good. But if I said I'm going to do it 1,000 times, now think about that for a moment. So I want to show you something. This is one of my favorite types of mathematics here. We're going to do several examples of this. But let's just say hypothetically, let me just make up a number. Let's say the probability of winning at a particular slot machine is, how about 0.005? No, actually, let's throw another zero. That's probably too high. There we go. 1 out of 2,000. That's you're going to bet your life on winning at this game, right? No, that'd be a bad idea. But if that's the probability of winning over a long period of time, if a lot of people are playing, shouldn't somebody win? Yeah. In fact, how often should there be winners?
1 in 2,000.
About what? Yeah. That's kind of. Now, does that mean if you do it 2,000 times, you're going to win? No. No, that's not what it means. But it means that if I'm going to do it 2,000 times, there's a high probability that I'm going to win. Because I could also win more than once, couldn't I? Now, the probability of winning at least once means, if, let's just say you're going to do this 1,000 times. So I'm asking you to calculate the probability you win once, or twice, or 3 times, ... 999 times, 1,000 times. That's 1,000 separate calculations, all of which we don't actually know how to do yet. We're going to learn that on the last day of this. It's using the binomial probability. It's really complicated. That's really complicated. Wait a minute. What's the complement of me winning at least once?
You not winning at all.
Me not winning at all. Me not winning at all means I do what every time? I lose. Oh. So let's call, by the way, this is universal stats language too. Little p we'll call the probability of win, and that would be, does anybody know what symbol we usually use for the other thing? You've had sets? We always use a little q. And p and q always add up to 1. This is universal. This is like 100-year-old stuff. We like to do that so it's consistent. Q would be the probability of losing. And that would equal 9995. Why? Because those two numbers have to add up to 1. You either win or you lose. If I said, what's the probability you win at least once? The complement would be the probability you win 0 times. So it means you lose every time. Okay? So, let's figure this one out for a moment. You're gonna play just for fun 1,000 times. All right, you got time. You're gonna play 1,000 because eventually you're gonna get, a tendonitis in your elbow from overuse syndrome. And make sure, by the way, when you're doing this, occasionally switch arms. You guys know this from carrying your backpacks, right? You don't always go the same shoulder because you're gonna have that huge buff left side, and your right side's gonna be, kind of skinny and weak. And I'd like to know, what is the probability we win at least once? Well, let's start by calculating the probability we win 0 times. So what is the probability of losing all 1,000 tries? No, all 1,000, attempts. Well, let's go back to a coin flip. If the probability of a heads is 1/2, what's the probability of a heads followed by a heads? It'd be 1/2 times 1/2. What's the probability of a head followed by a head followed by a head? It'd be 1/2 times 1/2 times 1/2. Why? Because I'm starting over each time. That's why the probability of having, a long string of heads is not very high, but the probability of each outcome was exactly 1/2. What is the probability you're going to lose? 0.9995. What's the probability you're going to lose 2 times in a row? That number squared. 3 times in a row? That number cubed. 1,000 times in a row? This is exactly the probability that you're going to lose all 1,000 times. How do I know? Because the probability remains the same each time you do it. It's not going to change. So everybody cool with that? I'm going to lose all 1,000 times. Okay? That's the probability of losing all 1,000 times. This is why I love this problem, because the math is actually really, really easy. So what is the probability of winning at least once? At least once is the complement of this, isn't it? Now, this goes back to our logic, right? There exists, the complement is there's none, right? There's at least one, the complement is there's none. So what is the probability then that I win at least once? 1 minus this. This is absolutely the mathematics. If I had said, what's the probability that I win exactly once? That's a complicated calculation that we haven't learned yet. That requires the binomial formula that we're going to do later. That one's actually complicated. The probability that I win a specific number of times is a complicated calculation. The only one that's easy is, what is the probability I win 0 times? What's the other easy one? The probability that I win every time, 1,000 times. Because I'm just taking the same number and raising it to the 1,000th power. Those are the only ones that are gimmies. Everything in between is complicated. But I said at least once, which means the complement is none. So let's calculate this. And by the way, are you going to give me a fractional answer here? Why are you not going to give me a fractional answer? Well, there's a whole lot of numbers in the denominator there, so probably impractical. So 1 minus 0.9995 raised to the 1,000th power. And this is I'm giving you a decimal approximation. We got a number?
I got 3935.
The question is always, how many decimals do you go? There is no absolute rule, but the standard, if you're in a stats class, does anybody know what the standard that everybody uses?
Is it 5?
Actually 4. Do you know why? Because the z-tables.
Oh.
Your z-tables give only 4 decimal place values, so therefore, to make it so I can work back and forth with z-tables, we typically go 4. Is there anything wrong with going more? No. Is there anything wrong with going less? No. If you said it's approximately 0.39, you didn't say anything wrong, because you indicated where it came from. Just make sure you round correctly. Now, your chances of winning are 1 in 2,000. But if I play a lot of times, all of a sudden my probability of winning at least once is not bad. By the way, that's at least once. That includes winning multiple times, doesn't it? Because it's saying my probability of losing every time is only about 0.6. Now, turns out they're playing not delayed. Meaning what?
More names?
We can play more times. So you're going, okay, my playing got delayed. Let's change the 1,000. Now I got, 3,000 times. So let's change it to 3,000 times. That's all you need is a cheap calculator. And now what's my answer? Approximately.
0.7780.
7769, so
Yeah,
777-ish.
Yeah.
Again, I don't care how many decimals you go. If you were a betting person, do you like that probability? This is your probability of victory, in other words. If you were, even if you're not a gambler, if someone said your probability of coming out ahead, let's just leave it like that, your probability of winning, coming out ahead is that, you'd say, I'll take those odds. Right, I'll take that probability, wouldn't you? Now, how many times do I have to play before the probability is 1? Infinitely many. Why? Because you're subtracting a positive number. You're never going to get to 1. Everybody understand that? But this is the complicated. We're not going to do this one exactly. Is there a number of times you have to play before your probability exceeds 0.5? Now, if you were a gambler, we're going to do a coin flip. Does anybody have an advantage? Okay, I always go heads, you always go tails. So we're just going to play for over and over again. You know, if I win, you pay me $1. If you win, I pay you $1. We'll play all day, and at the end of the day, we're probably going to break even, right? Probably. Certainly, if we play an even number of times, that seems reasonable. But that's what's called, and we're going to get to this later with expected value. That's what's called a fair game. A fair game is one where nobody has an advantage, where the probability of winning or losing is exactly the same, and in the long run, it's kind of a common sense thing. We're actually going to approach it mathematically later on. There's actually a formal way of defining it. But we'd say that's a fair game. What if I have a weighted coin or unfair dice that all of a sudden tilts the thing? But what if it tilted it in your favor? Then really, should you play the game? Well, the idea being, if I can win most of the time, all things being equal, I should play, because in the long run. Now, I'm not going to go into this part. This is something a little bit later on. How many have ever heard the term the law of large numbers? I hear people throw that around even in sporting events. The law of large numbers. People usually don't have any idea what that means. In simple English, if something has a fixed probability, a coin flip, and I do something a lot of times, I do it enough times, what I'm actually going to see as an outcome should match what I would have expected. Give you a simple example. If a coin has a probability of exactly 0.5 of being heads or tails, and I flip that coin 2 million times, and I actually kept track, by the way, am I going to get exactly 1 million of each? No, the probability of that's almost 0. But I should probably get something very close to 1 million of each. If I do the same thing over and over and over again, and again, we're going to get into this a little bit later, but I want to give you some simple examples because it might have affected you. How many have taken an SAT or some standardized test when you were in high school? Okay, now they've removed what they call the penalty for guessing. Did you know there used to be a penalty for guessing? How many took it when there was still a penalty for guessing? And here's the reason. Okay, I have, how many have ever taken an SAT prep course? Where you actually paid and you went and took the prep course? My son took the MCAT prep course, and they did a lot of practicing. A prep course generally is not designed to teach you information. It's designed to teach you how to take the test. In other words, how do I improve my score without learning more information? It's the strategy. Let me give you a very simple example, okay? If there are 5 responses, and only one of them is correct, but I learn how to eliminate, let's say, at least 2 of the responses as being just no possibility, they're terrible. I learned how to eliminate. I change my probability from 1/5 to 1/3. So if there were 15 questions and I randomly guess, and there are 5 responses to each question, I should get 1/5 of them right. Does that make sense? And we will show mathematically that's exactly what you should expect. I should expect half the time to get heads. If I'm guessing and there's 5 responses, I should be right 1/5 of the time. That just seems kind of a no-brainer. But what if I could change my probability to 1/3? Then I've increased the number of right answers, haven't I? By simply learning how to rule out bad answers. Okay, so why was there a penalty for guessing? It's real simple. On an SAT, I'll use it in overly simplified language. You got 4 points for every right answer. If you left it blank, nothing happened, but if you answered it incorrectly, you lost 1 point. A point was actually deducted. Because on every 5 guesses, the idea is you should get one of them right, and there's 4 points, but you got 4 of them wrong, subtract 4 points. So now you've got a break even. So the penalty for guessing was simply this: you should not be able to improve your score by guessing on all the ones you didn't know and therefore getting a few of them right just simply accidentally. And now you've got a higher score than you really know. So by penalizing you for guessing, you're going to get some right, but the number of points you lose from a probability standpoint should even it out. But again, if you can increase your probability of a right answer, what if you could actually, you were even better, you got to the point where you could eliminate maybe 3 answers. You're still blindly guessing, but now at only 2 responses. Then you should get about half of your guesses right, shouldn't you? And therefore you should guess, because your score is going to go way up as a result. That's how this was done for generations. I understand now they've removed the penalty for guessing. Okay? Which kind of makes the whole SAT prep course less effective, but still, if you learn how to guess better, you're still going to improve your score. But now there's no penalty. I taught the math portion of the GRE for a few years at San Diego State, and I would tell people answer as many questions as you could. There was no penalty for guessing. It's a scoreboard. It's simply based on how many right answers did you attain, not the percentage of right answers. If you guess on every question, or excuse me, if you attempt every question, but you're careless and sloppy and you miss 20% of them, then there's the other person who is slow and methodical and perfect on the half they guessed. They only got 50%. Person got 80%, far exceeded them. The idea was to get as many right answers as you could, not the best percentage you could. So that's the same kind of thing now on an SAT. Get as many answers as you can, don't worry if it's wrong. As opposed to being slow and methodical and not finishing. So this concept here of the probability, this is totally different. Now, where I first saw this, believe it or not, this mathematics was not in a math class. And this is something that I'm going to give you the exact example that this came from. There was a movie that came out, I want to say it was in the 90s. I always liked scary movies, Silence of the Lambs and things like that. This was probably the scariest movie I've ever seen. It was called Super Size Me. Has anybody ever seen that?
Yes.
Absolutely the scariest thing I've ever seen in my life. How many would agree with me? It was the scariest thing. Yeah, Super Size Me. It's a guy who wanted to show how bad fast food was for you. So what he did was he vowed, this is how it started. For the next 30 days, he was going to do nothing but eat fast food at a particular McRestaurant that I won't name because I don't want to get sued. But the policy that the McRestaurant had was they would ask randomly when you got to the front of the line, they would ask you, not every customer by the way, it was supposed to only be like 1 in 5. They would ask you arbitrarily, would you like to supersize your meal? And you'd say, sure, that meant I got bigger everything. Paid more money, of course. But they did not ask every person. That was the policy. It was supposed to be random. So what he also did was he not only ate fast food for every meal, if they asked him to supersize, he said yes, and he kept track of the statistics. And so one of the questions I would ask would be, well, if they only asked you once in 1 out of 5 times, then let's say you went 10 times, what's the probability that you supersized at least once? In other words, we do the exact same type of problem. And so this went on, and he kept track of his health concerns and all these things, and certain numbers went in very bad directions, and literally he became addicted. And then it went on from there to talk about school lunches. That was the scariest part. And literally nationally, they were talking about school lunches that were being provided was like the worst thing you could imagine. Everything was deep fried and reheated and frozen, and literally no food value in most any school lunches at public schools in the United States. He visited many. It was basically exposing, and a lot of things changed as a result. I mean, when my kids were going to school, the school lunches were actually quite healthy. They were also really expensive, but they were healthy. So the point that started with was if only a certain percentage are going to get asked a question, and literally they had I believe the person behind the counter had a clicker. Literally had a clicker. 1, 2, 3, 4. You're the 5th person I'm going to ask you. You're the 6th person I'm not going to ask you. They literally would try to do this. And so he would always say yes when he got there. But I think the number of times he got asked, the percentage for him was much higher than that. So that he questioned whether that was, or was he just unlucky enough to win, most of the time? Okay, so the probability of at least one It's really, really simple. So I'm gonna give you kind of a formal, because this is a special case. This is not all problems. So let's do this. P equals the probability, and in statistics we say, of success. Q is the probability of failure. Now, I'll define what that really means. Here's the only rules. P and Q have to be 1. P and Q are fixed. They cannot change, like the coin flip. They will stay the same. The probability of winning at the slot machine cannot change. Okay? Is everybody cool with that? Now, success and failure doesn't mean you succeeded or you failed. Whatever it is I'm counting, if it occurred, we call that a success. If it didn't occur, we call it a failure. So let's just say you're going to flip a coin 10 times and you're counting tails. And every time you get a tail, that's called a success. Every time you get a heads, that's called a fail. That's it. That's all that means. Okay? Again, it doesn't mean you succeeded or you failed. It just means the thing I'm counting happened versus the thing I'm counting didn't happen. That's all that means. So if this is the case, now we're going to do N trials. A trial is when I perform the experiment. Yesterday I said we're going to flip a coin 3 times. That means technically I did 3 trials. That's all that means. Okay? So N always refers to the number of trials. I'm going to do N trials, and the probability of success and failure are fixed. Then the probability of at least one success is 1 minus the probability of what? Of N failures. Okay, does that make sense? And we just did that a moment ago. If I want, I'm going to do something N times. If it makes it easier, think of N as being huge, not something small. I'm going to do something over and over and over and over and over again. I want you to fail at it every single time. That's the complement of it succeeding at least once. In other words, failing N times means you succeeded 0 times. So what is this probability? It's 1 minus what? Q to the nth power. Would you say that's a pretty simple formula? Yeah. Yeah, and it's kind of eye-opening because we don't always expect something like that. The numbers change really, really quickly as a result. Okay, because when I'm raising decimals to powers, they get smaller really fast. Okay, so everybody cool with that? So that I'm going to walk away from this one for a moment. We're going to come back and look at other things that are similar. How many have heard of the birthday problem? There's a classic problem. We're going to do that in a moment. If I said right now, I'm not going to do this. In a bigger class, I will actually do this. I'll say, let me pick every month. I'll write all the months, and then I'll say, if you're January, just holler out your date. I don't need to know your individual birthday, but we'll collect all the birth dates of everybody in the class. And if it's a fairly big class, we're not that big of a class, so it probably won't be true in this class. But it's really funny. It doesn't have to be a very big class, and I can almost guarantee you that we're going to see a repeated birthday. Now, wait a minute, there's 365 days, not counting leap year. There's 365 days in a year. If you've only got a handful of people, how could you possibly be certain that you're going to see repeated birthdays? And that seems like a common sense. The question is, how many people do you have to have before the probability is greater than 0.5? Turns out it's not that many. See, it's not, I'm not picking a day of the year, and I'm not even picking a person. So let's suppose there are N people, and you don't know anything, okay? An individual is chosen at random. Find the probability at least one other person has the same birthday. That's tough because, I mean, I don't know what n is. Doesn't matter, turns out. What's the complement of at least one other person has the same birthday? Nobody has the same birthday. Oh, I'm not looking at how many people, I'm looking at how many birthdays. So what we're gonna do is do the complement. It's gonna be 1 minus. Now, if I've only got one person, there's nothing to do, okay? But basically I have 365, 365, there's nobody else. Now I have a second person. What's the probability they do not have the same birthday as the first randomly chosen person, which could be any day of the year? 364 or 365. Now there's a third person. 363 over 365. Now here's where the n people come in. I'm going to do this how many times? N times. Oh, so what's this? Well, I think that's 365. What would this be? 365 minus n plus 1. Now let's actually use a value of n. It'll make it a little bit easier. But I want you to notice something about the numerator. You know something about my numerator? It's kind of factorial-ish, isn't it? It's kind of factorial-ish, isn't it? Do you agree with that part? What did that look like? I think yesterday. 365, 364, 363, 362. And I'm leaving out what? 365 minus n factorial. Wouldn't this be P 365n? We just did this last day, remember? This is exactly the probability that at least 2 people have the same birthday, because this is the probability that no 2 people have the same birthday. Oh. So in this case, it's weird because I said at least 2 people. In other words, at least one other person has the same birthday as randomly selected person. Because normally we'd say, well, what's the complement of at least 2? Wouldn't it be 0 or 1? No, not in that case. If I said, what's the, I want 2 of you to have the same birthday. 2 or more of you to have the same birthday. The only thing left is nobody has the same birthday. See, with your birthday, at least one other person means there's 2 of you with the same birthday. If there's no other person, then no people have the same birthday. So that's kind of a different use of the at least one, isn't it? Because now we're talking same as you. Now, everyone got out your calculators? Use 25. I'm just saying randomly, let's try 25. What'd you come up with?
143.
Did you 1 minus? You 1 minus. So at 25, my probability is about what? 0.5. Wait a minute. If there's 25 people in a room, the probability that at least 2 people have the same birthday is 0.57? Yeah. Turns out the magic number is actually 23. Now, does that defy common sense to you? See, the problem a lot of us have is we're thinking of a particular day of the year. No, I'm not thinking of a particular day of the year. I'm just saying any 2 people having the same birthday. So I'm not picking a day. So if I wrote everybody's birthdays down right now, how many do we have? 3, 5, 8, 10, 12, 14, 16, 17 including me, okay? Let's do this problem. There's only 17 people in the room, so this probability should be microscopic. There's 365 possible birthdays. There's only 17 people in the room. What's the probability at least 2 of us have the same birthday, okay? Oops. Anybody got a number? About 0.315. Wait a minute, that is almost, the probability is almost a third with only 17 people in the room that at least 2 of us have the same birthday. Isn't that crazy? Why is that? Because I'm multiplying by fractions that are getting successively smaller, meaning that this result is getting small actually fairly fast. So 1 minus is getting big. Now, this is one of these things I say, you know, half tongue in cheek. You're going to a party. You don't know anybody there, but you look around and go, there's 40 people at the party. And so you say to somebody, I don't know anybody here, but I bet at least 2 people have the same birthday. You bet them some serious coin. Most people say, yeah, I'll take that bet in a heartbeat. So you got 40 people at the party. You don't know any. You're walking into a room. Heck, you're at the DMV. Or, you know, you're waiting to be called. You know, you're doing your court duty, right? You're waiting to be called. There's all these. You're saying, there's 40 people. I bet you at least 2 people have the same birthday. Most people would take that bet in a second, wouldn't they? It's 40 people. There's no way. If there are 40 people, tell me what's the probability that at least 2 have the same birthday? Oops. It's got too big. No. Okay, is anybody's calculator able to do that? I was doing this on my titanium this morning. Okay, no one here has a graphing calculator? No, most of you, if you have a graphing calculator, okay, the number's really high, it's bigger, well over 0.7. Yeah, that defies common sense, doesn't it? But it's the nature of the problem. It's like the slot machine we just did a moment ago. The probability of winning once is ridiculous. Now, I'm going to ask you a question later on in the course about the lightning question, when we get to expected value. But you know, it's ridiculously small that somebody would actually get struck by lightning. But I said, what if you have a stadium full of people? What's the probability at least one of those people gets struck by lightning? It's actually pretty darn close to 1. The number can't be 1, right? Because you can never get 100%, or can you? Wait a minute. If I keep going, is it possible to get a numerator of 0 at some point? When would I get a numerator of 0? When n is 366. Is it possible to have I've got a stadium of 50,000 people. What's the probability at least 2 people have the same birthday? It's more like there's going to be hundreds of people with the same birthday, isn't it? So is there a point when you can guarantee the probability is 1? Yes, that's the last part of today's lecture. We're going to talk about that problem. So the next thing I want to talk about is the with and without replacement. This is not a complicated concept, but this is one that gives us trouble if we don't think about it. Okay, now I'm going to give you the most universally generic problem that we do in probability. An urn, U-R-N, sorry. An urn contains, let's say, 8 red and 12 blue marbles. This is one of the things that always made me laugh because I've had a bazillion stats, probability courses. They always use an urn. You're always choosing marbles out of an urn. Anybody know what an urn is? It's a jar where you put people's ashes in. Every statistics book ever written, every probability, there's always an urn. I just don't really get why an urn. Why not just a bowl? or a box. I have an urn filled with different marbles. Now, by the way, the blue marbles are indistinguishable from each other. The red marbles are indistinguishable from each other. But I can certainly distinguish the blue from the red. Okay? Everybody got that? So, you're going to choose one marble. Okay? Let's make it really simple. Let's call R the event you chose a red and B the event you chose a blue. Let's make it really simple. Then what's the probability of a red? What's the probability of a blue? That should be pretty easy.
0.6.4.
So it'd be 8/20 or 0.4 and 12/20. Okay, that was easy enough. Now I want to choose more than one marble. Here's where it gets a little dicey. All right. Now you're going to choose two marbles. Find the probability both are blue. With replacement, without replacement. This part now becomes critical. What do you suppose I mean by that? You're not grabbing two marbles at the same time. You're grabbing a marble, you're grabbing a second marble. That's different, isn't it? So I'm grabbing a marble, I'm asking what's the probability I get blue followed by blue? Well, this is like pick a card, any card that I did yesterday. After I pull out the marble, am I putting it back or am I holding on to it? Will that change the probability? Yes. So that's what these terms mean. With replacement means I put it back. And think of, I can't see the marbles. I thought, the probability of a blue is 100% because I'm going to reach in and grab a blue. No, I'm reaching in, I can't see what I'm grabbing. Okay, they all feel the same. With replacement means I put it back, which means I'm performing the same experiment twice in a row and nothing changed. Therefore, what do you think the answer in this case is? And we'll write it actually like this. The probability of blue followed by blue. What do you think that is?
0.36.
Oh, sorry. Wrong number. Do you agree it's 12/20 times 12/20? What do you think? Yes? No? Yeah. So however you want to simplify that, if you want to write it as a decimal, if you want to write it as a fraction. Okay? That's 3/5, I'll write it as 9/25. Now the second one is the probability of blue, but without replacement. Is it the same answer, first of all? Why is it not the same answer?
Because the probability changes when there's one.
Because the probability changes. So what's the probability of the second blue marble?
11/19.
Now why 11/19?
Because it's one less blue.
There's one less marble and one less blue marble, so 11/19. That is not the same answer, is it? So that would be, well, actually let's do 3/5. So that'd be 33/95.
Yeah.
Okay. Now, as a decimal, they're not exactly the same, they're close. But what if I said that we're going to continue doing this several times? And if I kept asking for blue marbles, that probability is going down, isn't it? Now think about this. You're a card player. What is the analogy to this in cards? We talked about it yesterday a little bit.
Outs.
Blackjack. If I just said in a deck of cards, what's the probability you were dealt an ace? Oh, okay. What's the probability you were dealt a second ace? A third ace? Does the probability change? Yeah, because I have a finite set of cards and you're not putting the cards back in. So the probability each time you are selecting a new card is going to change because there are less cards and there are less of that type of card. So that's how people actually do the calculations when they're doing card, is this same kind of thing. I am doing everything without replacement. And that's actually really important to understand because it does change the probability. And if I do something enough time, can I get a probability of 0? I want you to keep pulling blue marbles. Well, there's only 12. So if you have me do this more than 12 times, at some point my probability is 0 because there's no more blue marbles. But if I'm putting the marbles back, I can do this forever, can't I? All right, next question. Same question, choose 2 marbles. Find the probability, you're gonna like this one, this is not a common sense question. Find the probability the second marble is blue. Do you think I should consider with and without replacement again? Okay, let's do that. So with replacement. Without replacement. All right, let's do with replacement because that's easy. What's the answer with replacement? If you're thinking you're doing it wrong.
The same thing as the first one.
I'm putting the marble back after the first choice, so it's just straight up 12 over 20, isn't it? Does it matter if I said the second marble, the 15th marble, the 10,000th marble? If I'm always putting the marble back, then isn't the probability just gonna be 12 20s no matter what? So that one's easy. Without replacement, oh, geez.
11/19.
Well,
You have to count.
it kind of depends on something, doesn't it?
If the first one's red or not.
Is the first one red or is the first one blue? So I have to consider
Both of them.
cases. Oh. You have to. Because I need to calculate the probability of red followed by blue, and I need to calculate the probability of blue followed by blue. Does everyone agree with that? What am I gonna do with those 2 answers? Add them. Because these are 2 completely separate ways of getting to the same result that are mutually exclusive. There's no overlap. There's no way red followed by blue has an overlap of blue followed by blue. But does everyone realize there's 2 different ways that I can get a second blue marble? So I have to do both of these calculations. So what's the first one? The probability of a red followed by a blue would be
12 or
red.
8 over 20.
8/20ths times,
12/19.
good, 12/19ths, because there's still 12 blues, but there's only 19 marbles. Good, you guys caught that one. Second one. Blue.
12 over 20.
12, 20,
That is 11 over 9.
11 over 19. Now let's add those up. You can use your fraction key. So we'll go 8/20ths times 12/19ths plus 12/20ths times 11/19ths. And they add up to what?
0.6.
I'm gonna write this way. They add up to 12/20ths. Wait, hold on. The answer was the same. Whoa. That doesn't feel right, does it? That seems, wait a minute. I have an urn, it's filled with marbles, you're gonna pull them out with or without replacement, and I'm targeting the second marble. What's the probability the second marble is blue? Turns out it didn't matter whether it was with or without replacement, we just calculated. Probability of the second marble of blue is still just the probability of a blue marble. Isn't that crazy? Now, if I did this again, I said you're gonna pull out 3 marbles in a row, what's the probability that only the third marble you're looking at is blue? You know the answer is gonna be 12 over 20. With or without replacement, it's just without replacement, I have to consider all the cases, don't I? Red, red, blue, 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 red, blue. And when I added them all up, it would still work. Isn't this crazy? That it seems to defy common sense sometimes. But the with and without replacement is not complicated. You only have to take into account with replacement is a piece of cake because probabilities do not change. I'm doing the same thing over and over again. When we're flipping a coin, it literally is like a with replacement because the probability doesn't change. But cards are a great example because when you have the deck of cards and I'm dealing you the cards, and everybody here's played cards, right? You go fish, heck. When I'm dealing you the cards, do you look at it and hand it back as I'm going? Or do you have a collection in your hand at some point? I mean, all card games, don't you have a collection in your hand? So therefore, every probability would have to be without a replacement because I'm not putting any of the cards back as I receive them. So probabilities completely change in terms of how you do things. And it makes it definitely more complicated, doesn't it? Now, we're going to do the mathematics of poker. That's, I think the weekend lecture, because that requires combinations. I don't care if you're a card player. And it's really funny, I was listening to the radio, my radio, I know it's terrible. I have ESPN and NFL Network on TV, and my radio's always got 2 sports stations, depending on time of day. and the person was talking about poker, and was trying to relate it to something, and said something to the effect of, yeah, you know, I was working with someone the other day, they didn't understand it. They had a straight flush and I had a 2 of a kind, and that always wins. And I'm listening to this guy going, he's a blithering idiot. One is literally 1,000,000 times better than the other. I mean, one is the highest thing you can possibly get, and one's the lowest thing you can possibly get. And he's like, the crappy one always, and he's talking as an authority on, I'm like, oh boy, I changed the channel, I don't even listen to what this guy has to say about sports if he doesn't even know that. No, that's like saying the number 2 is the largest number in a deck of cards. But aren't there 3, 4, 5, 6, 7, 8, 9, 10? That's kind of what he was saying. But we're going to actually learn how to do these calculations, so you could actually say, oh yeah, a straight flush is the most valuable thing. Of the 2.6 million card hands, there's only 40 of them. It's extremely rare, and if you played the rest of your life, you may never actually get one. But if you got one, you're going to probably win, unless of course the other person's got the little deck in their sleeve, you know, like the old movies, right? The old gambler movies. So we've got this going on. Fairly simple thing. With and without replacement then are not complicated calculations. You just got to read the question. So if the probability is fixed, great. But if I'm doing something without replacement, then what's happening is my sample space is getting smaller. You never have to worry about that with coins, right? With coin flips or with dice rolls. But you would with cards, wouldn't you? You would with the marbles in the urn kind of thing. Because as I remove a physical object, it does change the probability. And we already did this when we were doing permutations. When I wanted to calculate what is the probability, or excuse me, how many different government groups we could have by choosing 4 people. So if you were my first choice, you were now removed from the group, weren't you? You could not be chosen again. So every calculation we did was already without replacement. And we calculated, oh, if I've got 20 people in the room and I pick you, I have 19 for the next choice, I have 18 for the next choice. We're already doing without replacement. What if it's a situation where we had some kind of a lottery going on and everybody bought lots of lottery tickets and we put all the lottery tickets in the bag? Could the same person win multiple times? Technically, yeah. Yeah, same person could win multiple times. But we typically think, okay, once you've won, we don't want to include you again, but there's nothing wrong with that. Okay, in statistics, we do what is called cluster sampling. How many have ever heard that in statistics? This is how you determine things like endangered species. What you do is you take a map, you literally divide the map up into a grid, maybe 100, maybe 1,000 little squares, and then you randomly choose some of the squares, randomly. Let's say you chose 3 of the 100 squares, so you chose 3% of the area. Then what you do with your entire team is you comb every square inch of that, and every time you find that particular animal, you calculate it. In the end, you found this many animals. You now can work backwards and say, this is our estimation of how many animals are in this whole region. Could you somehow run across the same animal twice? You calculate him this, and then he ran into a different region, you calculated it again. Is that possible? Yes, and we actually allow for that. Now, if you said, no, I can't have that happen, I can't count that animal twice, then you tag the animals. You know what that means? That's where you actually put the little band on them or something. You're not hurting them. So that way, when you run across it again, you go, okay, I've already counted this one. This is actually how it's done in real life. We do this in the ocean with certain types of fish that we believe are endangered, or we're just trying to figure out a rough count, like a body count. But the idea is the same. Am I doing things with replacement or without replacement? Because it changes the thing. Now, we're going to do the last piece. This is the easiest of all of the things that we do, but sometimes it's the most confusing. Okay? Let's go back to the birthday situation. If I gave you a certain number of, again, random individuals where you know nothing, can you calculate the probability that at least 2 people have the same birthday now? Absolutely. So you're showing up to a stadium full of people, and you want to calculate the probability that at least 2 people have the same birthday. 1. At what point can I guarantee the answer is 1?
That was 23. Or no, that was
That's better than 0.5. At what point can I guarantee the answer? Mesa College has tens of thousands of students. How many do you think have at least, what's the probability that at least 2 people have the same birthday? 1. Think of your calendar, 365 days. 25,000 people. Isn't there gonna be a day that has to have more than 1 person on it? Now, could everybody have the same birthday and we all skipped one day? Yeah. The point is, at what point can you absolutely guarantee that at least 2 people have the same birthday? Let's exclude leap year, because that's always confusing.
When you have 365.
366.
6.
Technically, the 365 could be perfectly spread out, but that 366th person kind of guarantees it, doesn't it? This is what is called the pigeonhole principle. How many have ever heard that term before? It's a goofy term. The pigeonhole principle. And I'll say it in simple terms, this is what it means. It comes from New York City when on rooftops, a lot of people, at least in movies, a lot of people, they have their pigeons. Everybody know what I'm talking about? You have these long row of like little pigeon houses, little pigeonholes, and the pigeons will roost there. If I have N pigeons and I have K pigeonholes, if N exceeds K, then there must be at least 1 pigeonhole with more than 1 pigeon. Is that about as ODA as it gets in math? I've got 50 perches, I have 100 pigeons. Doesn't have to be at least one of those perches that's got 2 pigeons. In fact, you'd say maybe several do, maybe 30 are in one. But the pigeonhole principle says if I have more things than there are slots to put them in, there must be a slot with it with more than 1. So I have 365 days on the calendar that a birthday could fall on, and I don't know when any of yours fall. But if there's 390 people in the room, there's 400 people in the room, there's 800 people in the room, there's got to be at least 1 birthday that has 2 names on it. Does that seem reasonable to you? So where it gets confusing is if I have less, I have to do a calculation. If I gave you less than 365 people and I said, what's the probability of at least 2 people having the same birthday, you got to calculate that. If I gave you more than 365 people. So let me do a similar question, all right? There are 1,000 people in the room. How do I ask this question? Do at least 3 people share the same birthday? Now I want you to think about that long and hard. I have 1,000 people in the room. Is it necessary that at least 3 people share the same birthday?
Yes,
Why?
because 365 goes into 1,000 more than 2 times.
Good. Perfect answer. At 730 people, it's mathematically possible that every birthday is occupied by exactly 2 people. That is not very likely, no, but it's possible, agreed? It is possible. But the 731st person has to now fall on a third person on a birthday. Okay? Is it necessary that at least 4 people share the same birthday? By the way, is it possible at least 4 people share? Heck, it's possible at least 10 people share the same birthday. But I'm saying, is it guaranteed? No, because 365 goes into 1,000 less than 3 times. So I could have every birthday, I could actually be doing it this way. 1,000 people are lining up, and they'll have amnesia. No one knows when they were born. So I'm going to assign you January 1st, I'm going to assign you January 1st, I'm going to assign you January 1st, and you're going to get January 2nd, and so on. Is it possible for me to get through all this without giving out in a single birthday 4 times? Yeah. I could have 2 on every birthday and 3 on the rest so that it adds up to 1,000. I'm being silly, but you guys understand. Mathematically, I'm saying, does it have to be the case? Yes, it has to be the case at 3, but not more than 3. Let's change the 1,000 now to 1,100. And now I'm going to change the 3 to a 4. Sorry, this is hard to read. I have 1,100 people, and now I'm asking, is it necessary that there's a birthday, or at least 4 people have the same birthday? You might need a calculator. Is it the case that there's a birthday that at least 4 people share? Is it an absolute money back guarantee? What do you think? First question was 1,000 people, 3 birthdays. Now I'm saying 1,100 people, 4 birthdays.
Yeah.
Why, Casey?
Because there's actually 1,096.
Because 3 times 365 is 1,095. That guaranteed that I can put 3s across the board, so the 1,096th person assured that there had to be a 4th person on some birthday. Everybody cool with that? That's kind of simple, isn't it? The pigeonhole principle, though, often gets confused with some of the calculations we do because we want to calculate things when we don't realize the answer is actually this easy, because it's a very different thing. But I love using it because you can answer so many questions. If I've got, let's say, 4 people, 5 people in a room, and I say, what's the probability at least 2 people were born in the same month? That's just like the birthday problem we did before, but instead of 365, I would use 12. I've got 5 people, what's the probability at least 2 shared the same month? I've got 13 people, what's the probability at least 2 shared the same month? And the probability is 1. Oh, 1 was a calculation, 1 was the pigeonhole principle. But do you see how I could easily confuse them because it's the same question, I just gave you different numbers? So when, again, there's more possibilities, 13 than there are slots to put them in, pigeonhole. When there's less, then it's calculation. All right, I'm going to bring up the practice test. Give me just a moment. Because we have a party tomorrow, everybody knows. It's a math party. That's the one you're encouraged to strut and show off and do all your cool stuff. All right, let's see who's coming. Here we go. It's taking a really long time. Where's the... Sorry, this is just taking this. It's housed with other people's stuff, so it takes a little while to get close all of their stuff. Okay, here we go. All righty. Make this a little bit bigger. Where's my, hold on, this is not letting me enlarge it. Oh, here we go. Perfect, okay. There are some gimmies, and there are some ones you gotta do a little work. Now, on the first question here, the Euclidean algorithm hopefully is fairly simple. Get out the calculator. Please don't do this pencil and paper. We'll make mistakes. But the follow-up question to this is what? This we did at the very first lecture. What's the follow-up to this question?
The linear combination.
Right, 11 is a linear combination of the original 2 numbers. And this is where when you're doing this, you actually probably want to include your scratch work separately, because it's the scratch work, remember, that when we put it back together. Hopefully you guys found that to be a fairly simple thing. And by the way, I recommend that you check along the way. Because as you saw, when the numbers start getting bigger, you're not going to be able to do it in your head conveniently. And if you make the smallest error, it's not going to work and you won't catch it until you're all done. And that is frustrating. But that's not complicated. It's an algorithm. I had asked a question yesterday. It was a good question. Someone said, so why are we doing this again? I said, because how many here right now are computer science people? Yeah, roughly about half of what I hear. Your ability to write code, yeah, everybody can write code. No, it's your ability to write algorithms. Algorithms are what you're going to be paid for when you have a real job and stuff. And the ability to write algorithms and understand them, this is not a do loop. Someone asked me, can I just do a do loop? Why is this not a do loop, computer programmers? It's not a complicated question. It's not a trick question. Do loop from I equal 1 to 10 do. Why is it not a do loop?
depends on the numbers.
Well, because before you start the problem, do you know how many iterations it's going to take? No. So it's probably a repeat until loop. You guys done things like that? Oh, repeat until what? Until the mod is 0. Okay, that's what I do on the first one, but then I can take the second one and say, it's a very similar thing. It's the repeat until I get back to the original. But the ability to write that simple type of program means that I can now give you absurdly big numbers. Does that ever come up? Yeah, data science and things like that. At San Diego State a few years ago, they had a new major started. It's called computational, computational sciences. And I worked with somebody who was actually, they were a Mesa adjunct and they went back to do this. And what they were learning basically was writing computer programs to do ridiculously large calculations efficiently. And so, something like that. But maybe they're dealing with numbers that are, let's just say lots of digits. Like too big to fit on your calculator, but still having to do things of this nature. You're not doing this by hand, right? The process might be a little longer, so the ability to write an algorithm, and by the way, I remember they were doing these types of problems exactly, literally on day 1 of the course. It was a graduate course. And it's very interesting because it's the same stuff I was teaching in this class, but they were doing it at a massive level, saying, yeah, we need to know how to do this for what we're doing. Now, the next group of problems, these are just, it's not the answer. Look what we did. I did a product, a sum, a combination notation. Just like, so we're familiar with these. These are not supposed to stump you in any way, but the first one's a product. Right? We have to understand, and the second one's a sum. They are not the same type of problem. And the third one is straight up combination notation. Now, a lot of you didn't like those types of problems because they seemed vague and ambiguous. Well, the idea anytime you're simplifying or evaluating is you cancel as much of the factorials as you can cancel. So that's why I ran down the first terms just enough so these were the same. Now, because I threw it over a denominator made it kind of cool, right? Because now I can cancel even more stuff. So the best answer I can give is something like my final answer. Factored or unfactored is not important, but canceling everything I can cancel would really be the main thing, okay? Now this is straight up the formula for a geometric series, isn't it? We did this before. This is called the nth partial sum of a geometric series. We know this is true. But to do the induction, now, in this case, the induction's pretty simple. Pretty simple. The first 2 steps of an induction problem are supposed to be no-brainers because you're not doing anything. You're proving it's true for the first case, which takes very little time, and you're stating what you're assuming. You don't have to prove it. You're saying, I'm going to assume that the following is true. Now, once you state that, use that in your answer. Now, in a sum, sums are fairly easy because the next term, the k plus first term, I'm just going to do the sum of the first k terms again and then physically add the k plus first. If this were a product, you would write the product of the first k terms and then multiply the k plus first term, right? So it's a very similar animal when it's a product. And then the goal at that point, after I've gotten to here, right? This is my assumption step. And by the way, a lot of you do this, I like this. You say this is equal to I equal 1 to k plus k plus first. So you actually write it out. That's a good idea. You don't have to, but that's really wise. So this is the sum of the first k terms, and this is the k plus first term if I substitute in. Now the rest is just manipulate the arithmetic. The best part is you know it's true. So if it's not working out, go back and fix the error. Don't fudge it. Don't make it fit, right? Do the algebra, make sure it works out. That works out really, really nicely. And then the final form is the original form with what? It's exactly the original form with with n replaced with, there's my original form. If I replace n with k plus 1, I don't need to replace it in the formula, I need to replace it in the result. Okay? So that's, I love those. And the next one was, we did 2 really different types. We did the sum and product, I lumped those the same because those are really, really simple algebra. Then we did the statement one. The statement one's a little bit trickier because a lot of times we aren't sure what it is our assumption. Where a lot of us got in trouble, we're saying this, but mathematically this doesn't mean anything. If I just say it mathematically, what am I actually assuming? I'm assuming this. I'm assuming there's an integer out there such that it equals 6 times the integer. That's what I'm assuming. So that somehow, however, most of you did a very good job of the manipulation. However you manipulated the arithmetic, people did a good job in general. If I make a mistake in the manipulation, it won't work. It won't work if I make a mistake, and you've got to catch it. If I made a mistake in the plus or minus somewhere in here, and all of a sudden I get to a point where I can't actually factor out a 6, then don't force it. Go back and fix the error. Because it looks kind of silly. On more than one case, a person, they made a mistake, it didn't work. They factored out a number that wasn't the right number, and then they just sort of, the 5 became a 6 in the next step because that's what it was supposed to be. Or when my answer was negative at the end, then I said it equals a positive number. We do that in calculus even, don't we? No, don't fudge it, fix it. All right, this one's a gimme. This is just, do you understand how to write a recursion? You got to get this one right. Even on the quiz, we struggled sometimes because we were too fast, too careless. And the next cluster of problems, again, this is just the definition of what these are. So I'm asking for a set. Where we get into a little bit of trouble sometimes is the, hold on a second. Actually, this wasn't the one. Most of you guys did a great job. When we're doing the Cartesian products, some of us are still not sure. A Cartesian product between two sets is always going to be an ordered pair. They don't have to be numbers. My first set could be shapes. Like, I have a triangle and a circle and a square, and my next set could be, Greek letters, and the Cartesian product would be ordered pairs in parentheses, square, comma, right? It doesn't matter what it is. That's all a Cartesian product is. It's just a set of ordered pairs, okay? That, again, that's supposed to be fairly simple. There's 2 questions that can be asked in this realm: containment or equals. They're really the same question. Equals just means I got to do containment twice. So don't worry about equals. That's irrelevant. Can you show containment? If I can show containment in one direction, let's suppose that's those are not necessarily equal, but let's just pretend for a moment those were equal. Then at this point, I am halfway done. So then I would start the second half, assume x is on the other side, and then most of you have figured out you're really writing almost in reverse, aren't you? You're writing a lot of the same statements when it's in equals.
Could you have let x be an element of A here, and you would still get 2 cases with the A intersection B and the A intersection not B?
I'm sorry, say it again.
So we started by saying x is an element of B or x is not an element of B?
Well, because I have B and B complement in the problem at the same time.
I guess what I'm saying is, do you have to let x be an element of A, or could you let x be an element of